Hello viewers, in today's session we are going to discuss another important and conceptual problem from definite integrals, and in this session we are going to evaluate this integral where we have the limits from 8 pi to 15 pi and the integrand is absolute value of cosine x, right? So let us call this integral as I, right? Now, in order to evaluate this integral, we have to make use of two important concepts. The first one is the concept of periodicity of functions, and then we'll make use of the concept of sign convention of trigonometric functions in four quadrants. So let us first denote the integrand by f of x. So f of x is mod of cos x, right? And we know that the period of mod of cos x is equal to pi, right? And from an important property of definite integrals, we know that if we have a periodic function, say f of x dx, and the lower limit is say p times t, and the upper limit is q times t, where p and q are some integers and t is the period of this function f of x. Then the value of this integral is given by q minus p times the integral from 0 to t f of x dx, right? So now if we compare this integral with this one, then we can see that t is the period of this function f of x, that is mod of cos x, right? So the value of t is pi, and here the value of p is given by 8, and the value of q is given by 15, right? So this integral I now takes the form that is q minus p times the integral from 0 to t f of x dx. So we have q minus p, that is 15 minus 8, and here we have 0 to pi, because the period of mod cos x is pi and f of x is mod of cos x, and here we have dx. So 15 minus 8 is 7, and here we have 0 to pi and mod of cos x dx. So now to evaluate this integral, we have to make use of the concept of sign convention of trigonometric function in four quadrants, and here the trigonometric function is the cosine x. Now see, if we have the four quadrants, here we have 0, here we have pi by 2, and then we have pi, this is 3 pi by 2, and here we have 2 pi, right? So this is the first quadrant, this is second, this is third, and this is fourth. And we know that the cosine function is positive in the first quadrant and in the fourth quadrant. So cosine function is positive in the first quadrant and in the fourth quadrant, and cosine function is negative in the second and third quadrant, right? So now here the limits of integration are from 0 to pi, right? So we have to go from the first quadrant to a second quadrant, that is from 0 to pi, right? And here we can see that when we go from first quadrant to second quadrant, then the cosine function changes sign from positive to negative, right? So at this point, that is pi by 2, we have to break this integral into two parts, right? So we have to now write here first integral, that is 0 to pi by 2, where the cosine function is positive. So here we have mod of cos x dx, and the second integral is from pi by 2 to pi, and here we have mod of cos x and dx. Now let us make use of the definition of a mod function. Now mod of p is defined as positive p whenever p is greater than 0, and mod of p is 0 whenever p is equal to 0, and mod of p is negative p when p is less than 0, right? So now if we replace p by cos of x, then the definition of mod cos x in the interval that is 0 to pi. So here we are considering only the interval that is from 0 to pi, right? So mod of cos x is positive cos x whenever cos x is greater than 0, and mod of cos x is 0 whenever cos x is equal to 0, and mod of cos x is negative cos x whenever cos of x is less than 0, right? Since we are restricting ourselves to the interval that is 0 to pi, when cos of x is greater than 0, it implies that x must lie between 0 and pi by 2, right? So when x belongs to the interval that is 0 to pi by 2, then cos of x is greater than 0. It means we are in the first quadrant. And when cos of x is equal to 0, it implies that x is equal to pi by 2, right? Because cos pi by 2 is equal to 0, right? And when cos of x is less than 0, it implies that x belongs to the interval that is from pi by 2 to pi, right? So this interval indicates the second quadrant, right? So in the first quadrant, cosine function is positive. At x is equal to pi by 2, cosine function is 0. And in the second quadrant, the cosine function is negative when x belongs to this interval, right? So let us here replace mod of cos x by positive cos x when x varies from 0 to pi by 2. So here mod of cos x is positive cos x, and in this case when x varies from pi by 2 to pi, mod of cos x should be replaced by negative cos of x. So now let us write the integral I as here we have 7, then we have 0 to pi by 2, and mod of cos x is positive cos x dx, and then we have pi by 2 to pi, and here a mod of cos x is negative cos x and dx, right? So now we have two simple integrals here. The integral of cosine x is sine x, and the limits of integration are from 0 to pi by 2. And then here we have the negative sign. The integral of cosine x is simply sine x, and the limits of integration are from pi by 2 to pi. So now let us simplify it. We have 7. The first will take here x is equal to pi by 2. So we have sine pi by 2 minus sine of 0. And then we have sine of pi. And then we have sine of pi by 2, right? Okay, so now here we can write sine pi by 2 as 1, sine 90 degrees is equal to 1, sine 0 is 0, and sine pi is 0, sine pi by 2 is 1. So we have 7, then we have 1, 1 minus 0 is 1, 0 minus 1 is minus 1, so we have 7, this is 1 plus 1, that is 7 times 2, that is equal to 14, right? So the value of this integral is equal to 14. Hello viewers, in today's session we are going to discuss another important and conceptual problem from definite integrals, and in this session we are going to discuss this integral involving the fractional part function. So we have to evaluate this integral in which the lower limit is minus 7 by 4 and the upper limit is 6, and the integrand is a fractional part of 4x, right? So here let us first call this integral as I, right? So to evaluate this integral, we have to make use of some important concepts from functions, right? And moreover we'll also utilize the concept of periodicity of fractional part function, right? So let us see how easily we can solve this integral using the concept of functions and the concept of periodic functions. Now let us first quickly see the definition of fractional part function, and we know that if we have a function, say y is equal to f of x, that is equal to fractional part of x, then fractional part of x is defined as the difference of x and greatest integer of x, right? So this is the definition of fractional part function, and we know that the period of fractional part function is equal to 1, so we can write the period t as equal to 1, right? Okay, now see here we have this function that is the fractional part of 4x, right? So if we take this function as the g of x, that is fractional part of 4x, then the period of g of x is given by say t1, then t1 is given by t by 4, because here we have the coefficient 4, right? And we know that if we have the function say f of x and its period is t, then the period of f of say ax is given by t by a, right? And here we write modulus of a. So if the period of f of x is t, then the period of f of ax is given by t divided by the absolute value of a, and here a is not equal to 0. Now see, for example, we know that the period of sine x is given by 2 pi, then the period of say sine 4x is given by 2 pi divided by a mod of 4. So here we have the coefficient, that is 4. So the period of sine 4x is given by 2 pi over 4, that is pi over 2, right? So this concept is utilized here. The period of fractional part of x is 1, and the period of fractional part of 4x is given by 1 divided by the absolute value of 4, and that is simply a t over 4, and t is 1, so we have the period of g of x as 1 over 4. So in general we can say that the period of fractional part of ax is given by t divided by a mod of a, and t is 1, so we have 1 over mod of a, and a is not equal to 0. So now let us write this integral I as integral from minus 7 over 4, and here we have 6, and fractional part of 4x can be written as g of x, right? Now let us rewrite the limits in the form, that is minus 7 over 4 can be written as minus 7 times 1 over 4, because 1 over 4 is the period of g of x, and here we have 6, So let us write 6 as 24 times 1 over 4. So we have now expressed the limits in this form. Minus 7 by 4 can be written as minus 7 times 1 over 4, and 6 can be written as 24 times 1 over 4, so that here we have the period of this function g of x, right? So now here we will utilize the an important property of definite integrals involving the periodicity of functions. Now see, we know this property, that is, if we have here p times t, and here we have q times t, and here we have a function, say g of x, right? And p and q are some integers, and t is the period of this function g of x. So this integral can be written as q minus p, that is difference of these two integers, times the integral, that is 0 to t, and here we have g of x dx. So now if we compare this integral with this one, then here the value of p is 7 minus 7, right? And the value of q is 24, and t is 1 by 4. So p is minus 7, q is 24, and t is 1 over 4, right? So here this integral, that is I, is now equal to q minus p, that is 24 minus minus 7, and here we have 0 to t is the period of g of x, and for t we can write 1 by 4, and for g of x we can write a fractional part of 4x, and here we have dx. Now this is 24 plus 7, because minus and minus becomes plus, and this is 31. So here we have 31 times 0 to 1 by 4, and fractional part of 4x can be expressed using the definition of fractional part of 4x. So here for x we can write 4x. So fractional part of 4x is now equal to 4x minus greatest integer of 4x, right? So now we have to evaluate this integral, and let us first concentrate on this term. Now see, here the limits of integration vary from 0 to 1 by 4, and x lies between 0 and 1 by 4, right? So x lies between 0 and 1 by 4, and if we multiply this inequality throughout by 4, then here we have 0 times 4 is 0, and here we have 4x, and here 4 and 4 get cancelled, so we are left with 1, right? So this inequality suggests that 4x, it lies between 0 and 1. So what we have done here, the limits of integration vary from 0 to 1 by 4. So x lies between 0 and 1 by 4. So if we multiply this inequality throughout by 4, then we get this inequality, and this inequality claims that 4x lies between 0 and 1. So by the definition of greatest integer function, anything lying between 0 and 1, the greatest integer of that term should be equal to 0. So here this term is equal to 0. So now we are left with 31, and here we have 0 to 1 by 4, and here we have 4x minus 0, because greatest integer of 4x is 0. So we have simply 4x, and here we have dx. Now we can take 4 outside the integral, so we have 31 times 4, and we have 0 to 1 by 4 x dx, and this is 31 times 4. The integral x dx is x square over 2, and the limits are from 0 to 1 by 4. So the value of this integral I can now be written as 31 times 4, and we can now substitute the limits and we can take the difference. So when we take x is equal to 1 by 4, here we have 1 over 16, because this is x square, and here the denominator is 2, and when we take 0, this term is 0, so here we have 0, right? So now we can solve it. 31 times 4, then we have 1 over 16 times 2, so this is 4 times 4 16. So here we have 4 times 2 8. So the value of this integral I is equal to 31 over 8, right? So viewers, this is how we can find out the value of this integral using the concept of fractional part function and the periodicity of fractional part function.